Hi everyone, and welcome to my Summer 2025 AgAid Internship Research presentation on guiding semi-autonomous pruning robots via torque feedback control in the absence of visual sensing. To touch on my background a little bit, I'm studying mechanical engineering at RWTH Aachen University in Germany, and this past year, I completed my double major in chemical engineering at Carnegie Mellon University. I started my work with agricultural engineering in high school when I built a fully automated hydroponic system that could regulate its own pH. This past semester in Carnegie Mellon's Robotics Institute, I helped work on a gantry robot that could extract DNA samples from tomato plant leaves. Then, at the beginning of this summer, I was employed at Virginia Tech to install another gantry-style robotic system integrated with a hydroponic setup, enabling real-time plant monitoring and digital twin creation for predictive growth modeling. This brings me to now, where I've had the wonderful opportunity to intern with Joe Davidson at Oregon State University's Intelligent Machines and Materials Lab through the AgAid program. The lab has been developing semi-autonomous pruning robots for specialty crops such as apples and cherries. The aim is to increase fruit yield by optimizing branch architecture. As global demand for food increases and labor shortages persist, improving agricultural efficiency through robots like these is becoming essential for sustainable food production. Throughout my internship, my work focused on the final motion planning stage, specifically guiding the robotic arm to accurately position the shears at pruning points initially identified through a computer vision algorithm. Here you can see recent versions of both Carnegie Mellon and Oregon State University's pruning robots. The main issue that these robots are facing is a failure to reach the pruning point accurately during the final approach stage. This is primarily due to the depth camera being offset from the cutting tool, causing the target branch to leave the camera's field of view as the arm moves closer. To address this, I began developing a non-visual closed-loop feedback control strategy to guide the shears precisely to the pruning point. The proposed method involves using torque feedback to adjust the final approach trajectory in real time, allowing the arm to essentially feel its way to the cut point while being able to sense and respond to slight movements of the branch as well. To do this, we need an accurate way to sense the magnitude and direction of forces exerted on the shears as they come into contact with the branch in order to adjust the robot's trajectory continuously. The Franka Emica robotic arm offers a key advantage for this application. It features joint torque sensors at all 7 of its joints and can publish this data at high frequency. This enables us to apply linear algebra and twist transformations to estimate the direction of external forces and compute the required joint velocities to dynamically adjust the end effector's approach trajectory. Because of this, we decided to transition our end effector from the UR5E to the Franka arm, so that we can take full advantage of this built-in joint torque sensing for precise force-based control. In addition to joint torque control, Franka is back-drivable, meaning external forces can physically move the arm, which is useful for detecting subtle interactions with the environment. In contrast, the UR5E is non-backdrivable, and while it does have a torque sensor at the wrist, the data is very noisy and essentially unusable for detecting the light contact forces involved in pruning. Also, the Franka has 7 degrees of freedom compared to only 6 on the UR5, giving it better reachability and flexibility around complex tree canopies. Therefore, we are working towards implementing the shear end effector on the Franka arm. To begin developing the controller, I worked in ROS2 with the Franka arm and collected joint torque data. I executed Cartesian motions using MoveIt through RViz and recorded the joint states topic during each trial. The data was saved to ROS bag files, which I then imported into MATLAB for analysis and visualization. Running these trials with the robot moving in free space, without any contact with the plant, allowed me to observe the internal joint torques generated purely by the robot's motion. Establishing this baseline is important because it helps distinguish normal internal forces from external forces due to interaction. By observing the arm's motion alongside the joint state data, I also learned how the Franka control interface handles trajectory optimization, for example, by favoring constraints such as maintaining constant angular velocities over executing strictly linear or Cartesian paths. Alongside my work on the actual arm, I began developing my own custom ROS2 controller package for simulation, planning, and interaction of a Franka arm model with its environment. Using MoveIt and Gazebo, I was able to get the simulated arm to recognize collision objects, such as plants, and respond to them appropriately. In the future, this will enable full path planning in the presence of obstacles so that the robot can safely navigate to pruning points on a real tree. The next step is to run physics simulations with the Franca arm on dynamic plant models that mimic the behavior of real plants. The arm should be able to recognize what it is coming into contact with, whether it be another branch or just leaves, based on the magnitude of the force sensed, and be able to make decisions on path planning to maximize manipulability, safety, and accuracy. In conclusion, the package I wrote and the work I did to get the Franca arm up to speed with the UR5E for implementation as a pruning robot's manipulator will support ongoing research and development by graduate students working on the robotic pruner here at Oregon State University. During my time here, in addition to my own project, I was honored to help collect data on blackberries out at the North Willamette Research and Extension Center farm. We measured the required picking force for a range of unripe to overripe blackberries by recording the maximum tension before detachment. This data allowed us to calculate the spring constants of blackberry stems. We also gathered data on each berry's size, weight, and firmness to identify further trends in required picking force and ripeness. This data will be used to design an end effector capable of identifying perfectly ripe blackberries and gently picking them without causing damage. A further advancement in efficient and automated farming. I want to thank the AgAid internship program for this opportunity and Oregon State University's Intelligent Machines and Materials Lab for having me. Special thanks to my advisor Joe and the people who I collaborated with in the lab, including Luke, Alejo, Scan, Farhan, Chelsea, Hannah, Pascal, and Cindy. Thank you also to Jordan and Paola for organizing and guiding the AgAid program.